Okay, so today we have two presenters, Patrick Miller and Denise Rothrock, who will tell us about the IASC program. Take it away.
Okay, thank you, Lisa. I'm Patrick Miller. I'm with the Department of Mathematics at Hardin-Simmons University, and today I'm going to talk about debris fields in the solar system, and also talk about dangerous threats that some of that debris poses to Earth. There we go. So we'll start off by talking about some historical events, some very far in the past, some quite recent, as a matter of fact. So let's talk about Vannevar, Siberia. 7 o'clock in the morning, 7:17 a.m. on June 30th, 1908. Just a typical day, everybody minding their own business. Man was sitting on his front porch of a trading post, just minding his own business. Suddenly he was hurled from his chair and experienced heat so intense that he felt as though his shirt had caught on fire. He was standing 70 kilometers away from the airburst of an asteroid that was 40 meters in diameter and weighed about 100,000 metric tons. The airburst that took place heated the Earth's atmosphere to over 44,000 degrees for a brief instant in time. That's about 4 to 5 times the temperature at the sun's surface. And it released an explosive equivalent of a 4 megaton hydrogen bomb, or on the Hiroshima-type bombs used in World War II, about 185 of those was the equivalent blast. Now, nobody, to our knowledge, was killed, except there were local deer and local elk. They were killed in the immediate blast area, and about 2,000 square kilometers of forested area was also obliterated. Some 80 million trees were stripped of their bark, just laid flat into the ground. So here's the pictorial of that. This asteroid, 30, 40 meters in diameter, weighing 100,000 metric tons, comes screaming in the Earth's atmosphere. It doesn't actually hit the ground. It airburst. As a matter of fact, the airburst did more damage than if it had hit the ground, with a 4 megaton equivalent amount of energy release. Now, it took about 20 years before anybody got up to Siberia, because this was an isolated region. And of course, in 1908, when this event took place, there weren't any trains, planes, or automobiles of note. So about 20 years later, in the early 1920s, the dog sled teams went up to the site, and this picture, along with the next picture I'll show you, are from that expedition. Those are some of the 80 million trees that were flattened by the airburst. And here was the area completely obliterated, the 1,600 square miles, 2,000 square kilometers region that was completely obliterated of all trees. Now, the event's called the Tunguska event, and there it is on a map. As you can see, it's in the middle of Siberia. In 1908, still didn't anybody live in that particular vicinity, although there did live someone 40 miles away who was knocked off the chair of his trading post. But if this thing had landed not at 7 o'clock in the morning, but had landed at noon, just a few hours later, it would have airburst over St. Petersburg. Now, St. Petersburg in 1908 had over 1 million people, and that blast would have killed probably most of those people. If that event takes place over St. Petersburg 4 or 5 hours later than when it actually took place over Tunguska. Or had it hit the Earth a couple of hours earlier, at 5 in the morning instead of 7 in the morning, it would have airburst over that small fishing village off the coast. And they had 1,000 or 2 people living in that village. So we were just fortunate that the event took place over an unpopulated area. Now, had it occurred later that night, it would have landed in the Long Island area, and that was in 1908, would have impacted 4.5 million people. And by the way, this event was a small one. Gulf of Mexico, 65 million BC. Asteroid 10 kilometers wide, that's about the size of a mountain, struck the Gulf of Mexico off of the coast of the Yucatan Peninsula, and it caused a crater about 360 kilometers wide, and it penetrated as deep as 35 kilometers into the surface of the Earth, and carved out this massive crater. That event is estimated to have released energy equivalent to 3 billion times the Tunguska event. So basically, imagine 3 billion 3 billion hydrogen bombs going off all at the same time, each with 4 megatons of energy. In this case, it had global consequences. The atmosphere thousands of miles away was heated at such a high temperature that any plants or animals that were in that zone were instantaneously ignited into flames and burned to death. Large amounts of sulfuric acid or battery acid was pumped high in the atmosphere. It rained down, very concentrated acid rain, and it killed plants and animals hundreds of miles away and dissolved rocks that were also hundreds of miles away from the impact site. It also placed tremendous amounts of fine dust into the Earth's atmosphere, and also had some soot from the fires that started that also were pumped in the Earth's atmosphere. And the prevailing winds over the coming weeks then would have spread that material all around the Earth. And the effect would have been to block light from the sun, darken the skies, and interrupting the food chain by stopping photosynthesis. And that would have taken place for several months, where the surface temperatures would have dropped below freezing. Now, when the skies did clear after that soot and dust finally settled down to the ground, the event also pumped into the atmosphere tremendous amounts of water vapor because it landed in the Gulf of Mexico, or it's the Gulf of Mexico today. And it also landed over, or impacted over, a limestone deposit and pumped large amounts of carbon dioxide into the atmosphere. What that would have done is caused a fluctuation in temperature in the other direction, where it became, the temperature became boiling and not freezing. And this huge fluctuation of temperature destroyed plants and animals all over the Earth, not just in the impact zone, where most of the devastation took place, but the effects were global, were worldwide. And it's estimated that 50% of the life on Earth died as a result of that mountain, that asteroid mountain impact off the Gulf of Mexico. And including, current line of thought is including the dinosaurs, although I've heard several geologists argue otherwise. But we do know that the dinosaurs show up in a record below this event and don't show it in the record above the event. So we think that that's a contributing factor to the destruction of the dinosaurs. So this is what it looks like today. It didn't look like this 55 million years ago, but this is what it looks like today. And there's the Chicxulub crater, or the Chicxulub event is what we call this, because that's the nearest city. And you can see that crater is overlaps the Yucatan and also the Gulf of Mexico. So a massive tsunami would have swept throughout the Gulf of Mexico from the impact. Plants and animals hundreds of miles to thousands of miles away would have burst into flames because of the intense temperature. Acid rain would have come down and dissolved the rocks and killed the plants and animals. Here is some geological sampling sites around that crater, showing you where they have found material from the impact. Actually, what they found were impact materials. These are little glass beads that were blown out, blew up in the atmosphere as molten material, and then when they fell back into the atmosphere, they quickly cooled down and showered these glass beads thousands of miles around that site. So you might say, well, why should I be worried about this? If you know who this person is, then that tells me how old you are. Denise, do you know who this person is?
No.
Okay. That's Alfred E. Newman from Mad Magazine. Anyway,
okay.
His famous statement is "What Me Worry." You might say, well, the event that could have destroyed a city, a major metropolitan area like Dallas or New York, that took place in 1908, that's over 100 years ago, and the event that destroyed half the life of the Earth took place 55 million years ago. So why should I be concerned about this? Well, let me introduce you to Apophis. In fact, you can see this. This is 3 pictures taken of this asteroid, taken over about a 1 hour time period, and then the pictures are lined up off star pattern. And near the middle of this, you can see the asteroid moving across the screen. Here's the orbit of Apophis about a year ago, showing you, here's Apophis there, and there's the Earth in its orbit. And right now, they're separated, and on this particular day, they were separated by about 50 million miles. However, on April the 13th, 2029, Friday, you'll find Apophis here. If you look behind it, you can see Earth. So on that particular day, Earth and Apophis are going to be at the same place at the same time. And Apophis will pass within about 20,000 kilometers of the Earth's surface, and that is closer than some of the, it is closer than the geosynchronous satellite. 7 years later, April 13th, 2036, let's talk about Apophis and the likelihood that it may impact the Earth. It's about 300 meters across. That's about the size of 3 football fields. And if it were to hit the Earth, the impact event would be equivalent to 130 Tunguska events. Remember, one Tunguska event would have destroyed New York City or destroyed St. Petersburg. This would have a regional consequences. This landed in Texas, for example, it would affect all the major metropolitan areas of the state, not just the place where it landed. So will Apophis hit the Earth? Yeah, probably will. Most likely will hit the Earth. Will it hit the Earth in 2029? Probably not. But I've got to tell you, there's enough uncertainty in the knowledge of Apophis' orbit to give it a possibility, a very slim possibility, about 1 out of 80,000 chance, that if it passes through a particular region around the Earth called a gravitational keyhole, its orbit will in fact be changed in such a way that it will in fact hit the Earth 7 years later when it sweeps by the Earth one more time in 2036. And this is the dotted or the red dotted region that you see there is where this particular asteroid would hit somewhere along that dotted red line. All I can tell you is that if Apophis gets its orbit changed in 2029, just a few years from now, and 2036, 7 years later, impacts Earth, you do not want to be standing anywhere along that dotted red line. Likelihood, about half of this you can see is over the Pacific Ocean, so that's probably where it would hit, although it could hit over Siberia, or it could hit over a land area here in Latin America and the northern South, just off the coast of Africa. But probably will probably hit there, about a 50% chance of doing that. If it does that, then that will cause tsunamis that will sweep the Pacific Rim, destroying the western coast region of the United States, destroying Japan, and destroying some of the New Zealand and some of the other land masses that you find in the South Pacific. Let's talk a little bit more recently. Planet Earth, February 15th, 2013. That's about 6 weeks ago. That time was last week. But when I wrote this, 6 weeks ago, the whole world held its breath as an asteroid designated 2012 DA14 passed within 22,000 kilometers of the surface of the Earth. That asteroid was 40 meters in diameter, and which makes the size of the Tunguska asteroid that airburst over Tunguska and Nichols Lake. And it also passed closer to Earth than many of our communication satellites. Had that asteroid arrived 15 minutes later, and it would have in fact hit the Earth's surface. Like I say, the event would have been as powerful as the Tunguska event. It turns out its trajectory was actually under the Earth's south pole, so the only land masses that would have been threatened had there been an impact probably been Australia, maybe southern parts of Africa. And had it landed in a large metropolitan area, just like Tunguska would have done, it would have killed millions of people. So give that some thought tonight when you're lying down trying to go to sleep. Here's a photograph or an image of the the orbits of that particular asteroid, where it was on February 15th. And as you saw, the one I showed you at Apophis, that asteroid and the Earth are at the same place at the same time. You'll also notice that it will cross the Earth a couple of times, and so the close pass will be repeated time and time again over the years. So it's just a matter of time before it actually. That was last week or last month. On that same day, a few hours earlier, in Chicxulub, Russia, 9 a.m. in the morning, start of a school day. The same morning that DA-14 just missed the Earth for 15 minutes, an asteroid that was 17 meters in diameter, weighing at 10,000 tons, airburst very close to that city. The airburst produced a shock wave that blew out windows and doors, and also collapsed walls of some buildings, brick buildings that were in the city. Over 1,200 people were injured, requiring medical attention, mostly by the flying glass and other debris from that shock. The explosive power, again, of that event was the equivalent of a small nuclear weapon, a small nuclear bomb, going off about 60 kilometers in the air above the city. Matter of fact, some people thought that's what was happening. They thought that there was a nuclear war had started, and this was a bomb that exploded near the city. First time in recorded history that I'm aware of that a large population of people were injured by an exploding asteroid. And so had this thing been a little bit closer to this city in Russia and not been off 60 kilometers away where it airburst, people would have in fact killed. It could have been much, much worse than what it turned out. And I can say that was just 6 weeks ago. So this is a very real threat. This debris from this asteroid debris that wanders in and around the Earth does hit the Earth all the time, and sometimes big pieces come through and pose a global-wide threat. More frequently, pose a regional or a citywide threat. Here's some pictures of the one over Russia last month. There's the actual airburst taken from somebody's dash cam. There's the contrail, or whatever, I guess, the struck to the atmosphere after it, or flew through the atmosphere after the airburst. Here you see, this was in a foyer of a office complex, and you can see the glass shards all over the floor. And there were people in that foyer at the time that this happened who were injured by the flying glass. There's a factory whose brick wall was collapsed as a result of the shock wave. And here's actually a photograph taken, I'm not sure from which satellite, it was taken from above the Earth, and you can see near the center here this bright light streak. That is the Chicxulub meteor or asteroid coming in and airbursting over that.
I love the fact that the weather satellite caught it. That's just fabulous.
Is that a weather satellite? Yeah. Okay. Yeah, you're right. So let's talk a little bit about what these things are that are airbursting over cities and posing threats to us here on the surface of the Earth. And as this is just much of a natural disaster happening on the Earth as a tsunami, killing tens of thousands of people, or earthquake destroying half of Japan, and tearing down some of their nuclear sites, it's a very real threat. Only this is the kind of threat that we can actually predict in advance. So we're talking about objects that look like this. Now these are larger than any of the ones that have hit the Earth in recent times. And Phobos, actually, this is an asteroid that doesn't threaten Earth. It's not near the Earth. It's in orbit about Mars. But I wanted to show this because this is about 16 miles across. Eros, which is the second image over, we've been to Eros. We've, I think in 2000, 2001, the nearest spacecraft went out to Eros and surveyed the asteroid. And then they actually dropped the spacecraft on the surface of the asteroid where it transmitted for a few seconds thereafter. The long side here is about 20 miles. The short side here is about 5 miles. Two others are Gasper and Ida. Ida, in fact, has a small companion. It's what we call a binary asteroid that they call DAC. And so these are large rocks, boulders of rock, some quite hefty in size that we're talking about here. Here's a flyby, I guess, on September 19, 2000, of the Arrow spacecraft that flew by the NEO, Near Earth Object Arrow. Now here's an image, probably the one on the bottom here would be a little bit easier to see and understand. This was, each green dot represents a known asteroid in the Minor Planet Center database as of September the 23rd, 2000, at Universal Time 1219. And you'll notice that this debris forms a ring around the sun, sort of a donut or core-shaped region around the sun. And it's located between Mars, which is this orbit here, and Jupiter, which is the outer orbit. But most of this stuff arcs out from the sun anywhere from 2 to 4 times, 2 to 4 astronomical units, or 2 to 4 times the distance between the Earth and the sun. But if you look carefully, you'll see a few green dots over here and a few green dots over there that are in Jupiter's orbit. Those are called the Trojans. Those have actually been pulled out of Jupiter's orbit out of the orbit of the main belt by Jupiter. And if you look more carefully in the interplanetary system where we live, you can also see some green dots there as well. There are literally thousands of them that have been dislodged from the main belt, primarily by Jupiter, and they're either pulled outwards or they're shifted inwards, and they come inward, and when they cross Earth's orbit, we see those, and those are the ones that the air burst over Chicxulub and hit and devastated the dinosaurs, and air burst over Tunguska and knocked the guy out off the air 40 miles away. That's referred to as the main belt, the main asteroid belt. The NEOs then are asteroids that were originally in the belt that have been dislodged gravitationally by Jupiter and sent inward and cross Earth's orbit. Those are the ones that pose impacts with Earth. And now here you have what we call the Trojans. These are the ones that have been pulled towards Jupiter that are actually in a region around Jupiter orbit, ahead and behind the orbit. But the main bulk of this material poses no threat to Earth, and it's located between 2 to 4 astronomical units from the sun, and that's what we identify as the main asteroid belt, or just the main belt. So now I want to talk to you about how NITARP is going to save the world by telling you about a program in which you can participate. It's the International Astronomical Search Collaboration. Now we call it ISAC. I realize that IASC doesn't spell ISAC, but that's what we call it. This was a program that was discovered or founded in October 2006 here at Hardin-Simmons University. As a matter of fact, an undergraduate student and I were sitting in my office one day and said, let's go look for asteroids. Didn't have the foggiest idea what that would mean to me 7 years later, and as I explained to you how that affects this collaboration. But it's an online educational outreach program in astronomy. It's for high schools and colleges. Using images that are typically taken just hours before at a professional observatory and distributed to the schools, the students then make original discoveries of asteroids. Most of these asteroids come from the main belt, but we have on occasion made some Trojan discoveries and also made some NEO discoveries. These discoveries then are officially reported to the Minor Planet Center at Harvard, which is the world's official repository of small body objects in the solar system, comets and Kuiper Belt objects, transcendental objects, and asteroids are all part of that that database maintained by the NPC. And also the NPC then reports any near Earth object discoveries to the NASA Near Earth Object Project, managed by JPL in Pasadena. When we started in October 2006, we had our first search. We had 5 participating high schools. Since then, ISAC has grown to more than 500 schools per year, and located, I say here, in 50 countries. It's actually located in more than 50 countries on 6 continents. And that growth has been primarily by word of mouth. Students during that time period have discovered 450 main belt asteroids. They've also discovered a couple of Earth-threatening NEOs, and 3, I think it's now maybe up to 5 Jupiter-Trojan asteroids. 22, it's up now to 26 main belt asteroids have been cataloged and numbered by the International Astronomical Union out of Paris. Once they're cataloged and numbered, and that process takes anywhere from 3 to 6 years, sometimes longer, then the student discoverers can officially name their asteroids. In fact, Denise will be talking here in a moment about Handstore's data. She and her students made a discovery in 2008. It got numbered last year after 4 years, and they named their asteroid after their high school, Madisonville High School.
Yes, I saw some of the press releases and I echoed it out to the NITARP gang, so they should have heard about it when it happened.
Good. Thank you.
Here's how it works. We have several sources, data sources. One is the Astronomical Research Institute, which is a survey program in Illinois. He'll produce a series of images over a course of an evening, and he takes them in groups of 3 of the same field of view, looking at the same spot in the sky, but the first image to the last image is a time gap of 30 minutes, sometimes 60 minutes. Now, over that time period, the stars' patterns don't change, but the asteroids can be shown to be changing their position with respect to those background star patterns. So those are put into school folders for the individual schools. For example, right now we've got 92 schools participating in 4 different campaigns, and each school has its own folder. Each school gets its own set of images. Kids come in the morning, students come in the morning to download the images. Then they use a program called Astronomical to search for and measure those asteroids. And if they make a discovery, then Minor Planet Center requires that within 7 to 10 days that a discovery, an initial discovery, a preliminary discovery, then is observed a second time. So you have to take a confirming set of images. And so we have another set of resources that will do that. We send a request to those resources, and they do the same thing that ARI does. They produce a set of images only 7 to 10 days later, pointing at the region where we think the asteroid is located, and download it using from their website or from our website and using Astronomical, take the measurements, and then those measurements, along with the original measurements of the discovery, then are forwarded to the Minor Planet Center and officially inserted into their international database. Here are some of the sites that provide us images. The Astronomical Research Institute provides most of the images that we get each year. He has a couple of telescopes, a 0.61 meter and a 0.81 meter telescope. He's about ready to start using a 1.3 meter that he's recently built and installed at his facility. This one is, and I'll talk a little bit more about this one in a moment because this is kind of special. This is a 1.8 meter PS1 telescope, or Pan-STARRS 1 telescope, located on Haleakala in Maui. Haleakala is the second largest mountain or volcano mountain in Hawaii. We also get images from the Mount Lemmon Sky Center at the University of Arizona, and this is a telescope we use there, which is a 0.81 meter telescope. In fact, we discovered a comet with that telescope last April, I think it was. And we also, this is primarily for the Chinese, work with the Xinglong Observatory, which is part of the National Astronomical Observatories of China, or the Chinese Academy of Sciences, and their 60-90 centimeter Schmidt telescope is to also gather images that are distributed to the schools. Now let me tell you a little bit about this one. This is Pan-STARRS. Pan-STARRS stands for Panoramic Survey Telescope and Rapid Response System. It isn't the largest telescope in the world by any means. As a matter of fact, we have 2 telescopes that we use for the FOX project, with even bigger diameter than that one is. It's run by the Institute for Astronomy at the University of Hawaii, but what it does have is the world's largest digital scientific camera. And this is an incredible camera at CCD. It produces images that stretch 7 degrees across the sky, that's in both dimensions, or it's 14 times the size of a full moon. So that means that one image you could lay out whatever 14 squared is, 156, 96 images of of a full moon. And each image contains 1.4 billion pixels, which is as much information as a DVD movie. And this telescope will take, it only takes 40 seconds to take the image, and it will take as many as 500 of them during the course of an evening. And so over a month, if the weather is cooperative, this telescope will survey the sky, the entire sky seen from Hawaii 3 times. And then you go in and you compare them. You look for things that change from one image to the next. You can find asteroids that are moving, supernovae are things they also look for. They look for outer solar system objects, the trans-Plutonian objects. Now this actually just changed. It changed a couple of weeks ago. After I made this slide, I say during one campaign, during a campaign, we get 1 image a week. We're now getting 2 images a week. So we're partitioning those images into 416 sub-images. And we distribute those 416 sub-images out to 60 schools around the world. From one sub-image, you typically get, or from one image, you typically get about 150 main belt asteroids. Last week, when we distributed the 2, we had over 1,600 asteroids that were discovered in those 2 images. In fact, when we were designing the EPO program for Handstore, we ran some test images, and on the very first test, we were only using 2. We actually get 4 at once from Handstore. If you look here, you can see the asteroid blinking back and forth. And up here, you can see another asteroid blinking back and forth. So we made 2 discoveries when we were just running a test. Now, as I mentioned to you, the Minor Planet Center requires that we do a follow-up 7 to 10 days. If we don't, then the students' discoveries, which were preliminary up to that point in time, are considered lost, and the discovery process has to start all over again. But we have a number of locations around the world that we use. This one is a network of telescopes, private network of telescopes, Parksville, called the Sierra Stars Observatory Network. We get about 5 hours a month on the Fox telescopes. Those are 2-meter telescopes. One's located on Haleakala, the same place as Handstore's one telescope is, and the other is located in Siding Spring, Australia. And we use this follow-up. This one's at Charleston State University here on the upper right, 32-inch or 80.81 meter telescope that we use for follow-up. But our workhorse is this one. This is the 1.3 meter robotically controlled telescope, which is managed by Western Kentucky University and is located at Peak National Observatory. And Western Kentucky University approached me in the summer of 2011 and said they had this telescope that was underutilized and wanted to know if we could use it. And I said, well, I can. So, to make a long story short, we wound up using this telescope, and we're now using it 40% of the time. Now, we did that kind of in a sneaky way. One of my data reduction volunteers wrote a program that goes in and looks at all the requests in the queue. And so as not to interfere with the professional research being done with that telescope, we request time on the telescope in between those professional requests. And that's allowed us then to use that telescope, be the biggest single user of that telescope, almost half the size. Now, if we have a slow mover or a fast mover, we have 3 other sites around the world that will, upon special request, do a follow-up. So they won't do follow-ups on main belt asteroids. So a slow mover would be an asteroid that maybe is a Trojan or further out. A fast mover would be a near-Earth object that poses perhaps hazard with Earth. Astronomical Research Institute provides us that kind of follow-up support. So does the Magdalena Ridge Observatory in Socorro, New Mexico, the 2.4 meter telescope. And then we have a series of telescopes that are at Schiaparelli Observatory in northern Italy. 0.61 meter and a 0.81 meter telescope, and they do follow up for special requests. So let me use this to bring my part of the presentation to a close here, so Denise can show you how to use astrometric and how to look for asteroids and how you can participate in the program. And we're delighted to have you. In fact, Vincent, Vince, are you with us?
Yeah, I'm right here.
He's been a long-time participant of ISAC, and his participation in ISAC led to a major research project involving orbits. He kept asking questions about orbits I didn't know the answer to, but he went out and figured out the answers, and he's developed quite a research project. Your latest paper is in Physics Teacher today,
right.
And so that's about ready to be published, as I understand.
Yes. It's going to come out on May.
Okay, in the May issue of Physics Teacher. So you need to look for that. Vince has an advanced copy of it. He sent me, and he indicated he would be happy to share that with you if you were so interested.
Yeah, I'm going to add it to Vincent's profile page on the brand new website here.
Oh, excellent. That's a very impressive project. These are some students who made discoveries. This is a high school student in Hyannisport, Massachusetts, who discovered an asteroid a couple of years ago. I sent her an email, and she got it, and telling her she had made this discovery. And she, it was kind of late at night. She was down in the basement working on her computer, doing homework, I guess, or texting or something. And as soon as she got my email, she started dancing around the computer, went upstairs, started dancing around her parents' television set. They said, "Well, what's wrong with you?" And they said, "Well, I discovered an asteroid." Later, the local astronomy club gave her an award, and she got recognition for that. These are closer to home here in Texas. This is a community college outside of Dallas. It's in the Spring Creek campus, Collin County. These are 4 community college students who discovered 3 asteroids during one of our programs. This is a group out of Brazil. That's Dr. Gustavo Rojas from a university in Puerto Alegre. He coordinates about 12 different schools that participate from Brazil. This is one of his teams at his local school that have gone out and searched for asteroids, discovered some. This is a group of students from Bulgaria. We work with an observatory in Varna, Bulgaria, that goes out and recruits schools throughout that country. And the stuff that she's recruited about 15 different schools and trained the teachers to participate in ISAC. This is the National Astronomical Observatories of China. This lady here is Hong Sin Gao, with a group of students. They're using astrometrics here. Now she's pointing to a bright star, so obviously she's not looking at asteroids. She's posing for the picture. But we have about 12 schools in the Beijing area that participate through her coordination. That participate each year in ISAC campaigns. Portugal, we have 50 schools in Portugal that participate. We have a group out of Lisbon called Nucleo that goes out and recruits schools throughout that country and also through the former Portuguese colonies in Africa that participate in ISAC. And each year they increase the number. This year it was 50. This is Shizuoka University in Japan. We don't have very many Japanese schools, but we do have a couple. This is another picture taken from Japan showing a large group of students who are working on astrometrics. A group of high school students in Broad Run High School outside of Manassas, Virginia. A group of students at the Thomas Jefferson High School located in Alexandria, Virginia. And I went, my student assistant and I went and visited both of those schools in 2010. And these are students, 3 students from Mozambique. Right now, in the current ISAC campaigns, we've got schools participating from Mozambique. They haven't made discoveries yet, but they've observed some NEOs and they've made some NEO confirmation mechanisms. They're coming along. India, we work with an organization out in New Delhi called SPACE, and that organization goes out and recruits schools from all around that country, and they participate during the summer months. And we'll have 75 schools starting May, about mid-May until mid-August from India that we participate in the ISAC campaign. One of our favorite countries is Poland. We have about 20 schools in Poland to participate, and we were given, this is an award ceremony at which a plaque was given to a student who made a number of discoveries several years ago. And this is a big deal. The entire city comes out and celebrates the event. the mayor's there, the cousins, uncles, and aunts, the city council, the school board, everybody's there. And see these students receive this award. Oh, I did forget to mention one thing to you before I close. Isaac is free. Could not figure out how to charge 3 students in Mozambique to participate in Isaac, so we just said we'll do it for free. And the reason we can do this is because no cost to participating schools is because Isaac is run by volunteers. And the resources that are provided to us are donated, with one exception, are donated. And it's this group of volunteers who manage the program behind the scenes and make this thing work. I just kind of keep things on track. They do all the work. And I haven't met most of these people. They've come to me through the internet and by word of mouth and said, well, I'd like to do something here. And so I arranged for them to, we've been trained and have them do that. They participate. And these are just some of the countries that, for which we have volunteers, in which we've got volunteers that support the Isaac program. So we would be delighted to have more NITARP teachers participate. We have several NITARP teachers in the past chapter. There are 2 groups in Hawaii that participate, and there's several groups in Illinois that have participated. Denise, of course, has participated. Vince has participated. But we're more than happy to have NITARP schools participate. And if they want to do that, then they need to contact me. And I will get you set up in a campaign so your students can also go out and measure and discover asteroids.
That's great. Excellent.
All right, so as I switch the control over to Denise, are there any questions you might have of me?
My guess is probably not. It may very well be that you get some email questions afterwards.
Okay, that's fine. Okay, so Denise should be coming up, and she's got us on the Isaac website. So Denise?
Hi. Again, my name is Denise Rothrock. I've been participating with Isaac since 2008. This happens to be my group of students that are on the front page of the website. This is when we gave our plaque to our school board when we named our asteroid Madisonville High. If you look here at the home page, there's a section called Astronomical. And this is where you can download the program. This program we use to find the asteroids. You can download the program. You can get a quick start guide, which gives you information, which will give you instructions on how to run Astronomical, to download it, and also how to tell between true and false signatures or true and false asteroids. There are some practices that you can also use. Disregard this down here. This is a separate program for neo-confirmation, so disregard the information down here. But this can get you started on setting up aspects and practice. These are the current campaigns that are going on right now. This is the Handstore campaign that Patrick talked about earlier. And you will find your school if you are participating. This is just a long list of the schools that are in the Handstore campaign right now. It started March the 10th, and it'll go to April the 14th. And right here happens to be my school. And when you click on it, there'll be a security code, but I've already opened it. And these are the 5 images that was displayed. And so you download those images. I usually put them on my desktop. I have a folder that I put all our images, that I download the images to. They are a zip file, so they'll have to fit. But if you'll note, these images here are the Handstore. These images up here I got from the international campaign that are from the ARI Institute, and these are different telescopes. The N numbers here tell you that this 24-inch telescope, the 30-inch telescope, 32. PS1 will start here. These are PS1 images. It's important to know what image that you're doing so that you can put the correct configuration file. So once you have your images downloaded and unzipped, then you can open Astrometrica. When you first open Astrometrica, this chart will come up. What it's doing is it's updating your MPC report, or MPC database. That is from the Minor Planet Center, where they keep a log of all the known asteroids. It's important to keep that up to date so that you're not measuring an asteroid that happens to be already known. So once it completes its update, then Astrometric itself opens. This is your toolbar, and to load into image, you go back down here. This indication down here, it tells me that I have PS1 configuration file open. If I was working on a different image, a 24, 30, or 32, I would have to change that configuration file in order to get the program to work properly. So I'm going to go ahead and load a Handstore's image set. This happens to be the one that we had last week that my students observed. You can see right there, there's a nice pretty little galaxy on this image set. What you need to do first, once you download your image, is you need to do what's called a data reduction. It takes the image and matches it to reference stars in the sky. So what it's doing now is taking these images and using a star catalog and making a match so that we know where in the sky these images were taken. As you can see, there are 4 images, and I'm not sure the timing between the images.
Did they go by pairs? There's 15 minutes between the first pair, 15 minutes between the second pair, and an hour between the pairs.
All right, this is a chart that pops up to make sure there's nothing in red. Otherwise, you've got an error that you have a 3-order fit. And so we have a good match to the reference chart. Back closed out. The next thing you want to do is you want to see if there's any known asteroids in this image set. We'll go back to Star Catalog, the MPC database, and it'll look for any known asteroids that have to be in this particular area. Take a few seconds. As you can see, there are 2 known asteroids. There's one here, there's one down here. So now we want to take these 4 images and we want to blink them. We want to make a loop. We want to make like a small movie. Okay. So what it's doing now is cycling through the 4 different images. 1, 2, 3, 4. And what is going to appear, and I'm just going to zoom in on this so we can see it a little bit better, the stars will appear to stay stationary. I start up here in the upper right-hand corner. Stars will stay stationary, and as you can see right here, we have a moving object. So we have to measure that moving object. What I'm going to do is I'm going to stop. These buttons right here are your advanced stop, just like they are. I'm going to magnify it so it's really good and put my cursor right in the center of that asteroid. Okay. What you want to make sure that you have a really nice fit. This is one that's pretty good. Your SNR is greater than 5. The visible magnitude for this particular asteroid is 20.4. We also want to make sure there's nothing close by, or there's nothing around this, or there's this not known asteroid. Pretty well know that it's not because it's not numbered. But these indications are asteroids that are somewhere around there, but there's nothing that is exactly right where we are. So that this is a new asteroid. But what we're going to do is we're going to put in our special for each school. Mine has the MHS, which is Madisonville High School, and then a 4-digit number. If they keep a log in a journal as to what image sets they're doing, what numbers have been used, and then when the next asteroid is found, they take that next number that's available. Then you have to do this on each image set, or each image in the set. Same number. You do this for each image. Now, if it's an ARI image, they will have 3 images. In case of Handstores, there are 4. Got some more. Now, if it's like close to the edge, you can only get 2 or 3 of the images, not all 4. That's okay. You can't send in 1 measurement. Okay. All right. So once you finish that, then you can continue on and sweep the image, look for other unknown asteroids like that one was, or measuring known asteroids. Okay. This one here is known, and we also know it's not measured because it has a red square pointer. So you do the same thing again. Image 1. I just like really good. My hash mark's really good on the center. Very nice. ISR. Okay. This particular one, we know is a known asteroid because it's numbered. So if we can see here the right ascension and declination, 0, 0, which means at that location, this is the asteroid at that location. So we're going to click OK on that, and it's going to put in the information here. We're going to accept, and we're going to do that on all 4 images. I usually pair my students up for 2, and we rotate around so that everybody has a chance to analyze the image. It's a fairly easy process. It's just a matter of knowing what is an asteroid and what's not. What you want to look for is you want to look for this round shape. You want to make sure that it is moving in a straight line and at a constant speed, and also the visible magnitude is not fluctuating very much. This is where we are. This is go forward. So you're going to scan the entire image and look for either known asteroids or hopefully find you some unknown asteroids. Let's do the motion again. Okay, so this asteroid, it's got a nice round shape. It's moving in a straight line, and it's moving at a constant speed. So if we go over here to file, if we have finished the entire image, then we're ready to make our MPC report. This is the first measurement I took here, and this is the second one here. Okay. What you have to do is you have to copy your MPC report and place it into a notebook or notepad.
We're suddenly getting a lot of lag here, but I think we can still follow.
Okay, shall I slow down just a little bit? Are we okay?
I think we're okay.
And you change the measure to your students, you're going to have up to 5 students. Okay. And in the end, you put your initials of your high school or school. What image set?
So you misspelled the name of your school?
No, and Madisonville High School. Oh, I did it. Sorry. Conde Station. Sorry. Image set. This was a gift one. Okay, and the only other change you have to make is you have to space out your asteroids. So once you've made these changes, your MPC report is ready to be saved, and it's sent to Dr. Miller at the ISAC, to his ISAC email. Okay, and that's basically all you have to do in analyzing an image. Anybody have any questions?
What do those numbers mean?
The numbers here, of course, these are the designation of the asteroid. This is the one that we named that we feel that is an unknown asteroid. Same thing here, this is one that was designated for this particular asteroid. This is the date. This was March the 6th, 2013. And this is the portion of the day time. I do believe it has to be converted into an actual time of day that it would take. This right ascension index, this is your magnitude, very nice. They're not fluctuating greatly, so that's a good sign. And this right here is the observatory's code, the code for the observatory in which the image was taken. Okay, and that's the basic MPC report that gets mailed and then gets forwarded on to the Minor Planet Center.
That's great. Very cool.
Okay.
So I will send this around to the NITARP folks, and if they have any questions, if the people that weren't able to attend live have questions, I guess they can email you at the email address you put up right there, or they can. I'll include that email in the email that I send around. So great. Thank you guys very, very much, and especially for interrupting your spring break. Denise, to participate.
That's fine.
Thanks a lot. You will be hearing from me.